Hello, and this is our second lecture regards to IIR filter designs. So in the previous lecture, what we did was the impulse invariant design. We basically were doing, we were matching the time response of the filter. In this one, what we're going to be doing is matching the frequency response of the filter, and this lecture focuses on the bilinear transform instead. So we know that the Z transform and the S transform are linked together by this equation here, where Z is equal to e to the power st. And if we rearrange this to make S the subject of the formula, we'll get this form here, where S is equal to ln Z divided by t. However, S in this form is very difficult to substitute into any equation to make it in terms of S, to transform it in terms of Z. What we're going to do here is that we're going to use a first order approximation for the exponential function using the Maclaurin expansion, and basically we can say that e to the st of s can be equal to this form here, and then it can be equal to this form here as well, which is approximately equal to z. And because this is approximately equal to z, we can now make the approximation that s is approximately equal to 2 divided by t on s, all multiplied by z to the minus 1 divided by z plus 1. In generalizing this means that s is equal to c of this term here, where c maps to 2 divided by t of s. And this form here for mapping the s transform to the z transform using the Maclaurin expansion formula is referred to as the bilinear transform. So the bilinear transform basically matches the frequency response. What we do is that instead of the analog filter matching from negative f of a to f of a, which is going to be the analog cutoff frequency, and that this varies regards an analog, the digital frequency range is going to be minus f of s divided by 2 to f of s divided by 2. And we fix that digital frequency range, where f of s is referred to as our sampling frequency. In fixing the frequency range, we need to make sure that we avoid aliasing as well. So we need to make sure in the design we adjust the frequency range to match to the Nyquist theorem accordingly. The overall objective of the bilinear transform is to map the analog frequency cutoff into the digital frequency range for that filter that we're designing for. S here that we saw in the previous slides were regards to positive powers of Z, but we can also rearrange this to get negative powers of Z accordingly as well. Either way, S in these two forms is acceptable, and they don't make much of a difference regardless when you're doing substitutions, unless we ask for a anti-causal filter or a causal filter design accordingly. Now, once we have S in this form here, what we basically want is h of z, where we transform h of s here by substituting this s form here into h of s to get it in terms of z accordingly. So basically what this does is that at some analog frequency f of a, which was the response of h of s, this needs to map onto some frequency f in the digital plane for the digital filter. What we basically notice that in doing this, at that analog frequency, s of a is equal to j omega a, which is j 2 pi fa, and we know z here was equal to that exponent form, so we can substitute t of s into 2 pi f t of s here. Z be equal to that, we can map z here accordingly to this form here. But this was regards to s and so forth, and we say s was equal to c of this, and we're going on, and then we can rearrange and simplify this entire equation to get our f of a equation here accordingly. So in doing the bilinear transform, it's important to memorize this f of a equation because we're going to have to calculate for this accordingly, where f here would be the frequency that we're trying to solve for, and f of s is going to be the sampling frequency. We can also recall that 2 pi f divided by f of s is also equal to the digital frequency. So the f of a equation can be simplified into this form here. And typically when a question comes and it gives you the digital frequency, it's going to be in radians per second. So you can just substitute the radians per second value straight into here without trying to calculate 2 pi f on f of s. So the purpose of this f of a equation here is that yes, you'll be given the analog frequency, but we need to solve for what the c constant is. when we're going to be doing the substitution of S in order to make the S equation in terms of Z. So what this equation does is that it maps the analog frequency to the desired digital frequency through this C constant instead. And because we have this tan function here, this is going to be a non-linear relationship between the analog and digital frequencies accordingly. So as such, when the analog frequency is 0, the digital frequency is going to be 0. But however, as the analog frequency tends towards infinity, the digital frequency tends towards pi. So the entire infinite frequency range in analog, meaning from negative infinity to positive infinity, will compress into the digital frequency between negative pi and positive pi. This effect is what we refer to as warping. And the reason why it goes into this range in the digital frequency range, remember, for every 2 pi cycles, the signal keeps on repeating itself. So the design steps of the bilinear transform is that we first choose our appropriate analog filter. We match the analog frequency and the digital frequency using the f of a equation here, as seen in this green block. We then rearrange it accordingly and calculate for C. And once we have C being our constant, we substitute for S using the bilinear transform. So actually, let's watch this in a physical example. So the first example here is that we're going to have to require to design a digital filter using the bilinear transform, where the response is going to be at 3 kHz, and we're going to be matching the analog filter response at omega A equal to 4 radian per second. And we have our analog filter prototype equation here accordingly. We are also given f of s here being equal to 12 kHz. So because we have the equation already, what we're going to have to figure out is how do we solve for C. So the first thing is that we start with the f of a equation that we had from before. So f of a is equal to C divided by 2 pi tan of 0.5 capital omega. We know capital omega here is equal to 2 pi f divided by f of s. And we knew I had f, and we had f of s from before, so this is going to equate to 0.5 pi. In case you're wondering how we got 0.5 pi here, let's go back a few slides. F of s here was 12 kHz. F here, was 3 kHz. So we put the 3 divided by 12, we get 1 divided by 4. And then, when we are here, this 2 pi will be multiplied by 1 divided by 4, so that will give us half pi, which is equal to 0.5 pi. Because we have capital omega here now, that means we actually could solve for C. So f of a here was also 4. So 4 divided by 2 pi equal to this here, and we solve for C, so we end up getting C is equal to 4. Let's backtrack a little bit. Remember, we had omega A here equal to 4 radians per second, so that's how we were able to extract our f of a accordingly. So C here is going to be equal to 4 accordingly. And now that we have C is equal to 4, and we're designing for a low-pass filter, we could say S is equal to 4 multiplied by Z to the minus 1 divided by Z plus 1. Once we have this form here, we substitute it to the h of s. And once we substitute the form here, and we expand out and put it into standard form, we have our final answer here accordingly. The response of the IIR filter looks like this, where basically we can see that the magnitude response and the phase response basically are going to have a non-linear relationship altogether, because of that approximation that we just noted. In the comparison between the analog filter and the IIR filter design, we basically can see that the magnitude response somewhat remains the same. But the frequency part here, what we're watching, is that this is 4 radians per second here, but this also maps to 3 kHz here accordingly as well, which gives you an idea how the analog to digital mapping is satisfied accordingly. If we also watch for the impulse response here, this gives us an idea of how it actually truncates about 10 sample periods accordingly as well. And this being so because for infinite impulse response, remember this response just keeps on going forever. So for us to truncate it, to map the analog frequency range to the digital frequency range, we say, okay, we take a certain amount of samples here in order to get this approximation and truncation accordingly. the canonical representation of that equation in this yellow block here would look like this here. So the bilinear transform design we saw there was basically if we did for a low pass filter design. What happens if we have to do a high pass filter design? So the impulse invariant technique that we saw in the previous lecture, it does not map any analog low pass filter to a digital high pass filter very well. And this tends to create unstable designs, and when you actually watch the pole zero plot, the poles tend to be outside of the unit circle accordingly. However, the bilinear transform does allow for the mapping of an analog low pass filter to a digital high pass filter, but a slight modification is required with regards to the S equation and the F of A equation. So if you're designing for a low pass analog to a low pass digital, we still maintain our equations that we've seen throughout the entire slide so far. But if we're designing for a low pass analog to a high pass digital, the equation here flips accordingly. So instead of z minus 1 and over z plus 1, it's now going to be z plus 1 over z minus 1. And the f of a equation now becomes negative c divided by 2 pi here, and it's going to be cotan of 0.5 pi. Cotan is basically 1 divided by tan of the same part inside the brackets here. So we're going to repeat example 1 here for a high pass filter of the same cutoff frequency. So we start with the f of a equation here accordingly for the high pass filter form. From before we saw that capital omega was 0.5 pi. In solving for c, what we're going to find here is that in doing this equation we're going to get c equal to negative 4 accordingly. Because c is equal to negative 4 and we're using the high pass version, instead of this z minus 1 is going to be on the numerator, it's now going to be on the denominator, and the z plus 1 here is going to be on the numerator. We substitute this s form here into the h of s equation, and we get our h of z equation accordingly. Because this is in the causal form, we need to make sure that it is anti-causal form, basically where we have no delays being positive. Once we have it in this form here, we can standardize it accordingly by making sure that this part here, on the denominator, is going to be 1, and we divide all the terms accordingly by 7. The standard form tends to be our final answer for any impulse invariant design or bilinear transform design that we're doing accordingly for any IIR filter. So the response here basically shows you that instead of it being this way instead, it's going to be the opposite way, that it's going to be from 0 and it goes up accordingly for the high pass filter design instead. So for a low pass filter design, it will start at some value and it will go towards some negative value here. But a high pass filter design will start at 0 and then it goes up to some value here accordingly as well. One thing to note though is that this here is also maintaining the nonlinearity because of that approximation that we did from S to Z. And in comparison, the low pass filter design, it goes downwards, but the high pass filter design goes upwards instead. So this brings us to the end of our second IIR filter design example. And the last lecture with regards to IIR filter design will do more examples as to how you actually can solve equations and design IIR filters accordingly depending on the type of design method required. Be it that it's the impulse invariant design technique or that it's going to be the bilinear transform technique.